I mentioned that these partial derivatives can be easily calculated numerically. And we will now examine how we do that. And we will use for that the so-called Kragten approach. So that the model that in our case looks like this, we will calculate all these components numerically so that eventually we will arrive at exactly the same result via the same kind of calculation. Our aim now is to calculate numerically the uncertainty component for our uncertainty estimation, whereby the most important thing is numerically calculating the partial derivative. And let us start by writing out the function. Our output quantity is calculated by some function from a number of input quantities. N different input quantities. And let us examine, for example, the uncertainty component corresponding to the input quantity number 1. All others go just the same way. So the uncertainty component reads like this. The uncertainty over the output quantity that is caused by this particular input quantity. And is calculated like this. And whenever we calculate numerically partial derivatives, we replace these infinitesimally small changes or infinitesimally small deltas by finite deltas, so that the essence of approximation that is made in this case is the following. Now, with delta x1, all is clear, but how do we find delta y? For this, we have to look at this function again, and it is obvious that we have to subtract from the function found at position x1 plus delta x1, the function as it stands here, whereby x1 has not been modified. So, delta y is calculated as follows. So that we subtract just like this. And now we can substitute this delta y here so that the uncertainty component calculation will read as follows. So, and now an important thing in numerical calculation of partial derivatives is how do we choose which value of delta we use here. And what Kragten proposed, and this is why this method carries his name, he proposed that let us take the delta equal to the standard uncertainty of this input quantity, so that we can use like this. And the beauty of his proposal is that these two now cancel out. So that eventually the uncertainty component is calculated as follows. And this is the way the Kragten approach works. And we will now illustrate this by calculating, as a concrete example, the result, the uncertainty of our particular ammonium determination example. We will now carry out this uncertainty estimation using the Kragten method on the example of the same data that we have in our ammonium example. And in this file, I have compiled already the input data, the values of the input quantities, their standard uncertainties, their units. And just to remember, I have also brought here the model equation and also the equation according to which we calculate the standard uncertainty. And this Kragten method most conveniently is used using a Kragten matrix. But before we can move to Kragten matrix, we have to calculate the value of the output quantity or calculate the value of the result, so that we calculate this Cn sample value according to the model equation that we have. And this means that, first of all, from A sample, we subtract B0. Then we divide this by B1. Then we multiply this by the dilution factor. And finally, we add here the delta CDC, which, if you remember, takes into account some additional uncertainty sources. And this value, as you can see, is just the same as we had in the slides. You may wonder, why do we use in our calculation this value at all, because it is 0? But it will become obvious quite soon that it is essential to include it also here in the calculation. And now we can build the so-called Kragten matrix, which is a matrix of equal column and row length, and both of them have to be equal to the number of input quantities that we have, which in our case means that we have a 5 to 5 matrix. Let us somehow denote it. And also it is useful to mark the diagonal cells of this matrix, and this will become obvious quite soon why this is useful. We can paint them gray. All right. Now we will take the values of our input quantities into all these 5 columns, just the same way as they already are in this column here. So equal, and we use the $sign to fix the column, but we do not use the $sign so that we don't want to fix the row. And now we copy this into all these cells, but we use for pasting the so-called paste special, meaning that we only paste formulas but not formats. This way we can preserve these diagonal elements and also the borders. And what we will do now, we will now change the diagonal elements. So all the elements here that have not been painted gray, we retain as they are, but to all the diagonal elements we add the respective standard uncertainties just the same way as they are here. Plus d6 plus d7 plus d8 plus d9 plus d10. So we see now that each of these columns in principle contains the same values as we have in this column here. But in each column, one of the input quantity values has been changed by adding the standard uncertainty. And now into these cells here, we will compute the value of the output quantity using these input quantities here. And we can conveniently just copy this formula here. Okay. And if you now look carefully, you see that all these values are very similar to this one, but they are all a little bit different. And they are a little bit different because in all cases one of the input quantities was changed. And now also it becomes obvious why it was important to include this quantity into the equation, because even though here, 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 and here it's all 0, but here it's not 0 anymore. So it has to be included into equation. And as I told during the lecture, even though this quantity does not influence the value of the result, it does influence its uncertainty. So we can here now write again Cn sample. And here now come delta Cn sample values. These are now the same delta values that I just showed on the whiteboard. So from each and every one of these, we subtract this value from cell C12. And again, we have to fix C, but we don't really need to fix 12. Okay. And these deltas actually are our uncertainty components. So these uncertainty components here are actually their approximations. And these values here already carry also some information about their respective magnitudes, how large they are. And now, as we have the uncertainty components, we only need to use this formula for calculation. And we calculate the squares of all those uncertainty components. Okay. We simply multiply them by themselves to make it easy. And now we have to sum up all those squares. And now the square square root of this value actually is our standard uncertainty. And this we can already calculate into this cell here. And we can see that this uncertainty is exactly the same as we also saw in the slides. And let us put also the unit. So that this is the value and the standard uncertainty of our result. The Kragten method is also very useful because the data that we now have here enable us very easily to calculate the uncertainty contributions of the input quantities, or the uncertainty indexes as they are also called sometimes. If we look for a moment at the lecture slide, then you saw that I explained here that a sample carries this weight, roughly 36% of the uncertainty, CDC roughly 33% of the uncertainty. Let us now see how do we calculate these. This calculation goes actually very easily. The uncertainty indexes are calculated by ratioing the squared uncertainty component under question to the sum of all squares of all uncertainty components. And this can be very easily done here. So, uncertainty contributions. And we simply divide this square by the sum of all squares. But since we want to copy, it is useful to fix the column. And we copy it all the way here. These uncertainty components now have been expressed as simple ratios, but we can also express them as percentages. And we don't need so many decimals here. So, and it's in fact from this kind of calculation, these data that you can see here originate. And as was explained in the lecture, all the effort should be devoted to minimizing the uncertainty in a sample and also in delta CDC, because it is these components here that determine most of the uncertainty in this case. We can now also make here a nice presentation of the result as result with uncertainty expressed as expanded uncertainty, and also a correct number of digits here. So let us write here we now take this value here. Here we insert the plus minus symbol. And here we take the standard uncertainty multiplied by 2, which is the coverage factor. And of course, here we will need also the units, which in our case are milligrams per liter. And let us now look at the decimals after the comma. Here we have the first significant digit 1, meaning we have to give 2 significant digits, which is exactly the case here, which make it 3 digits after the comma, so that we have to modify also here to make 3 digits after the comma. And we also have to give some further information about coverage factor and about the distribution function. And we can write here k is equal to 2 and norm. And in this particular case, we can assume normal distribution, because as also was explained in one of the lectures, if we have more than 3 dominating components, and here we have 4, it is fairly safe to assume that our result is distributed normally, and K2 in that case corresponds to roughly 95% of coverage probability. So you saw now how numerical calculation of uncertainty components works according to the Kragten approach. And it's a good approach in the sense that it is completely universal and also can be applied to very complex types of models. In fact, our model is fairly simple, and analytical derivatives would be fully possible to calculate in this case. But very often, model is quite complex, and analytical derivatives cannot be easily calculated. But for Kragten approach, this does not matter. This approach can always be used.